So measurements and problem solving. Chapter 1, you guys need to go over on your own and do the homework for chapter 1 in Mastering Chemistry by Sunday. Again, chapter 1 is sort of like, welcome to chemistry, and here's the scientific method. And it's sort of like the same intro that you find in every text. So we're going to skip over that and just start lecturing with chapter 2, which is all about measurements and problem solving, working with numbers, getting comfortable with numbers and units and things like that. So whenever you look at a number, or really a measured number, the last value in that measured number has a certain level of uncertainty to it. So an example of that is measuring global temperatures. These slides are pretty old, but they say that the average global temperature has risen 0.6 degrees Celsius in the last century. When they say 0.6, what they're saying is that it's 0.6 plus or minus 1 degree Celsius. So it could be as high as 0.7 or as low as 0.5. So just know with measured values that there is a certain level of uncertainty, because we are only as good at measuring something as our equipment is, right? It is depending on what thermometer they had, where they were sampling, how many samples they got, precision will increase or decrease. Okay, in chemistry, we're going to be dealing with really, really big numbers and really, really small numbers. And it can be extremely cumbersome to write those numbers in what we would call decimal form. Decimal form is what you're used to seeing a number in. So the full extended number with like all the zeros and everything. So what we'll do is we'll write these decimal numbers in scientific notation. And scientific notation is an abbreviated way to get a really, really big number or a really small number in a more concise way. There's going to be two components to your scientific notation. You'll have a decimal part. The decimal part has to lie between 1 and 10. Really, it needs to lie between 1 and 9.999. 99999. If you get to 10, you would drop it down to 1. So the decimal one, you kind of, when you have your original number, and we'll go through this, you want to find a way to move the decimal in such a way that you get something between 1 through 10. Now, because we're moving the decimal, we need to preserve the magnitude of the number. Like, how big was that number originally, or how small was that number? Get in the habit of looking at the sign on the exponent. If it's negative, it means it's talking about a really teeny tiny number. All right. If it's positive, it means it's talking about a big number. So this right here would be a small number. A positive exponent means that we're taking our decimal and we're multiplying it by 10 times whatever that exponent is. So if it's 10 to the first power, it would be multiplying it by 10 or moving the decimal over 1. If it's 10 to the third power, it's multiplying it by 1,000, or like having to move the decimal over 3 spots to make the number as large as it actually is. The opposite is true when you're dealing with a negative number, or a negative exponent rather. We're going to be dividing by a factor of 10. So 10 to the negative 1 is really 1 divided by 10, or a decimal move in the smaller direction. 10 to the negative 3 is 1 divided by 10 times 10 times 10, or again, 3 hops, 3 movements in the smaller direction. So let's see an example of this. Well, I guess to convert a number to scientific notation, first find the decimal part. So you'll be given a number. You want to find the decimal part that lies between 1 and 10. Then move where the decimal is currently living, which is usually at the very end of the number, to that new spot. You'll count how many hops it takes to get to that new spot, and that will be the number that you put as the exponent. If it's a big number, positive. If it's a small number, negative. So let's look at this here. This would not necessarily be a number I'd write in scientific notation, because it actually has more characters written in scientific notation than it does just by itself, but that's what they used here. So we've got 5,983. The decimal lives right there. Okay, they haven't put it in there, so it's just inferred that it's there. We want to move this decimal to a place where we will get a number between 1 and 10. Well, that's going to be right there. All right, so now we have 5.983. But we don't want to just stop there, right? We're trying to consolidate this number, but we need to preserve how big it is. This number is in the thousands place. So we add the exponent times 10 to the, and it's just going to be the number of hops that you took from your original place of the decimal point to the final place. So we had to hop over 1, 2, 3 hops. All right, 10 to the third. If you're representing a big number, keep that exponent positive. What if you have a smaller number like this one, a decimal? Well, here's the decimal place. Again, remember the first part of our scientific notation, we always want it to lie between 1 and 10. So I'm going to move this decimal at its current location over here between the 3 and the 4. That will give me 3.4. Count how many hops it takes. 1, 2, 3, 4 hops to get to its new decimal location. And it is a small number. So we're going to put a negative in front of it. So 3.4 times 10 to the negative 4. So start getting in the habit of looking at something like this and realizing, oh, that's a large number, and looking at something like this and saying, oh, that's a decimal or that's a small number. So let's do a couple of these. I'm super angry that I don't have my whiteboard. What other app can I use? I can use notes. Notes. Okay, well, I don't want all this stuff. Let's try this out. So let's say we have a number that 4. Sorry, this until I get the whiteboard, this is a little bit harder for me to write straight. 4, 8, 7, 2, 6, 5, 0, 0, 0. Okay. I want you to try and write this in scientific notation. 4, 8, 7, 2, 6, 5, 0, 0, 0. I did have 2 questions. One said, if I may clarify, we don't count the 0 before the initial decimal point in the example. No, we don't include that 0. And then I thought there was Zoom had a built-in whiteboard. I totally forgot about that. Let's see if that's the case. Well, let's work on this one and then we'll play around with that. So the decimal is currently hanging out right there. We need to get a number between 1 and 10. So the decimal needs to move here. 4.8725. Okay, I'm not going to include those zeros because they're not significant, and we'll talk about what significance means or sig figs a little bit later. But for now, we just need to move this decimal over. So 1, 2, 3, 4, 5, 6, 7, 8 hops. So times 10 to the 8th. This is a big number, so we are going to go with a positive 8. Any questions on that? You can throw it in the chat or pull your mute off. Okay, hold on 1 second. I'm gonna share this. All right, yeah, let's try this. Okay, so 0.000001, 2, 3, 4, 5. Let's get 6 zeros, a 4, a 0, and a 7. Okay, I want you to write this number in scientific notation. I'll give you all 45 seconds. All right, so our decimal is, when you have a decimal number, it is easier to see where it is, right? So it's living there. We want to move it to this spot here. All right, so we'll have 4.07. That lies between 1 and 10. Why wouldn't we go with 40.7? Doesn't lie between 1 and 10. Wouldn't want to go with 0.407, kind of overshot it. So this is where we're sticking. Let's hop our decimal 1, 2, 3, 4, 5, 6, 7 hops. So times 10, the exponent will have a magnitude of 7. And because this is a small number, I'm going to give it a negative value. So 4.07 times 10 to the negative 7th. This is especially useful when we get into like really, really large and really, really small numbers. So I'm actually going to give you two things written in scientific notation, and I want you to expand them back out into decimal form. So let's do 4.81 times 10 to the negative 8th. And then let's do Avogadro's number, which is 6.022 times 10 to the 23rd. This is a number we see quite often in our chem class. I'll give you all, I don't know, a minute and a half, 2 minutes to work through both of those. Remember to be asking yourself too conceptually, am I trying to make a small number or am I trying to make a big number? So hop in the direction that will yield which one you want. Okay, so for the first one we have here, we're trying to make a small number. The negative exponent there is indicating that. So I'm going to write the 4.81 kind of over here. So this decimal is going to need to get moved to the left or in the direction that creates a smaller number by 8 hops. The first hop is going to take into account that number between 1 and 10. The remaining 7 hops are going to be filled with zeros. So I'll have 7 zeros. 1, 2, 3, 4, 5, 6, 7, and I'll put the decimal. If you want, you can, fill all the hops in like this, and then just put all the zeros in there. Okay, so 0.00000000481 would be the decimal form of this. Avogadro's number, super large number, I'm going to write the 6.022 over here. So in order to get past the number, I need to take 1, 2, 3 hops, all right? 3 hops out of 23 hops. So I'm going to have 20 more hops, and every one of those hops is going to be filled with a 0. So I'm not going to put all the hops. I'm just going to add 20 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's what the number looks like if you were to add some commas, right? To try and give it like a little bit more meaning. But it's a big freaking number. This is a perfect example of why we like scientific notation. I don't want to write this a million times. Any questions on going back and forth between scientific notation? What that scientific notation means? Okay, cool. So let's go back over to the slides. Kind of already talked about this, but anytime you're looking at a scientific number or a measured number, know that that last value is always an estimated value. So in this number here, we have 4 digits that we know are certain, and the last digit, the 5th digit, is estimated. If the number had a lot more digits to it, you still only classify the last digit as the estimated digit. So this number could be as big as 45.873 or as small as 45.871. Whoever was measuring it or whatever piece of equipment was measuring it felt that the 2 was the most appropriate place to put it. The greater the precision, the more precise a number is, the more significant figures you're going to have. So a significant figure is a number within a measurement that tells you something about how precise it is. Okay. Any non-zero numbers, like all of these are all significant. It's usually the zeros that get us into trouble. Let's look at a couple different examples of how we can know certain digits, and then we have to kind of guesstimate the second one. So here's a scale with this like suspicious blue substance on it. I just rewatched Breaking Bad with my husband last week. Yes, we did it in a week. Such a good show. So good. So anyway, when looking at the scale has marks at the every 1 or single gram. So 1 gram, 2 gram, 3 grams. So when looking at where the line is, I can see that it passes the 1 gram. So I know for sure that I have a value of 1 in the ones place. Now, you can, quote unquote, guesstimate 1 past whatever your smallest tick mark is. So somewhere between the 1 and the 2 is where our line lies. And I'm kind of guessing that it's at like, it's not halfway, it's like, 2/10 of a way or 1/5 of a way through. So we'll get 1.2 grams. You guys hear that screaming? Yeah, that's my 1-year-old daughter. Again, husband duty. Yeah. All right, so 1.2. What if we had a more precise scale? We're measuring this cute little pistachio here. This scale has measurements that go not just to the ones place, but to the 10ths place. So we know for sure we've passed the 1 gram, right? So this is a certain number. And then we've got these baby ticks that are at the 10ths place. And I know that I go 1, 2. I don't quite make it to the 3, somewhere between 2 and 3. Okay, so 1.2, these are both certain. Okay, hold on one second. This is like comical. My 1-year-old is literally screaming at the door, yanking on the handle.
Miss Henderson, I think you're still muted.
Thank you. I'm going to say, if you're wondering if I'm sitting on the floor, I am sitting on the floor. Yes, I was sitting at a desk all day and it was killing my hips. So I'm sitting on the floor for this lecture. All right, so we know for sure the ones place is a 1. We know for sure that the tenths place is a 2. Then we get to guesstimate. So we get to guesstimate the 100th place, or somewhere that lies between those 2 tick marks. And in this case, they say, hey, it's like halfway, but just a little closer to the 0.3 tick mark. So they give it a 6. All right, if your scale continued to get more precise, you had more of these tick marks, you could extend this out, right? And have a more precise piece of information. We like precision, right? This is kind of a crappy scale. This is a much better scale. The scales that we have in our labs at AV Tech go out to the 4th decimal place. So even more precision, we like that. So how we can tell, how precise a number is by quantifying or looking at the number of significant figures that it contains. What classifies a significant figure is a digit or a number, or a digit within a number that tells us something about precision. It's not just telling us about magnitude. We're not using it as a placeholder to tell us how big or small the number is. It's actually telling us something about a measured amount. So the first rule is really easy. All non-zero digits are significant. So if I have a number like 38156. How many significant figures does this thing have? 1, 2, 3, 4, and 5. I would say 5 sig figs. All of them are non-zero. Those are really easy. It's the zeros that give us a little bit of trouble. So let's start talking about zeros. The first one are interior zeros. So interior zeros, or zeros between 2 non-zero numbers, are always significant. So if I have a number like 3, 0, 0, 0, 0, 3, the 3 is significant. The other 3 is also significant, right? And then all the zeros in the center are significant. So significant, 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 significant. So 1 to 6, 6 sig figs here. Significant figures are a representation of precision. So we can't be talking about how precise a number is, and then all of a sudden it's not including anything with precision. And then we go back to talking about how precise a number is. It happens in a bracket or a grouping, right? There's a clump of precision. It's the things on the tail end or the front that give us a little bit of trouble. So internal zeros, significant. Trailing zeros. Zeros to the right of a non-zero number that fall after a decimal place or decimal point are significant. So I'm going to write a number a couple different ways. So let's say we have this number here, 4. How many significant figures does this thing have? Pretty easy, 1 sig fig, right? 1 sig fig. Well, instead of writing it as 4, what if it was written as 4.0? This thing has 2 sig figs. Okay, according to this rule that we're talking about, zeros that come after the non-zero part of the number and after a decimal place are significant. So this 4 is sort of loosey-goosey. It's like, yeah, I don't know, it's like 4 grams or whatever. This is like, no, it's 4 grams to the 10th place. All right, if I had something like this, 4.0000, how many sig figs does this thing have? This has 5 sig figs, 5 sig figs. This is like an extremely precise 4. So, we would prefer to have something like this or a scale that can produce a number like this versus like kind of a crappy 4 like that. But scales that produce this many decimal places are more expensive. So. All right, let's look at some of the other rules. Trailing zeros that fall before a decimal point are considered significant. So trailing zeros means that they're after the main number, but they fall before a decimal point. So if we have, let's see here. Three, 2, 0, 0.00. This is significant. This is significant. That's kind of easy to identify. Remember, zeros that come after the decimal place, after the main number, are significant. And then according to this rule, zeros that come after the main number but before a decimal place are also significant. So we would say that this has 6 significant figures. Also, these zeros in the center, remember, we're not going to have significant, insignificant, and then significant. They'll always be sort of bracketed or clumped together. Going along with number 4, let's skip to number 5, number 6. Trailing zeros at the end of a number but before what's called an implied decimal point are ambiguous and should be avoided. Okay, so if I have a number like 6020000, I know that the 6 is significant. I know that the 2 is significant. And I know the 0 in between these are also significant. Where am I unsure? These zeros here. I don't know if they're significant. I don't know if they're telling anything about precision. I don't know if this is like, oh, it's 602,000 in a casual way, or if it's like exactly 602,000. I can't tell the way that it's written here. If instead it was written like this, 602, 000, and they put a decimal there, that would indicate that all of those things are significant just by having that stupid decimal written in there. Okay, because what that tells you is that those zeros should be counted in your level of precision, that your precision is going to the ones place. What if like only one of these zeros was significant? Like let's say, for instance, this 0 was significant, but not these 2. How could you get around that? You could write the number in scientific notation, and I could write it as 6.02 and just include the 1 0 times 10 to the 5th. Okay, that's a workaround so that I have 1, 2, 3, and 4 significant figures. So if I have like, 8 million, but there's no decimal there, like let's say this is 8 million grams. I don't know if it's 8,400,020 grams. I have no idea if any of these zeros are precise or if we've just sort of rounded. So in this case, we only have one significant figure. It's just the 8, 1 sig fig here. The last rule Leading zeros, zeros to the left of the first non-zero number. So any numbers that are in front of your like meat, the meat of the number, are not significant. All they're doing is serving as a location for the decimal point. So this is something you'll see when you are working with oops, sorry. When you're working with decimal numbers. So let's say we have 0.000501. Where does the actual number start? It starts right at that 5. Okay. Why this thing keeps snapping off on me? There we go. So we start at the 5. The 5 is significant, the 1 is significant, and the 0 in between is obviously significant. What are these zeros doing here? They're not telling us anything about precision. They're just in a space to let us know how small the number is. Precision is something we tack on the end of a number, not in front of the number. So if we had a number like 0.00200, the 2 would be significant. These zeros would also be significant. These zeros are not significant. Why are these 2 zeros significant? Because they're telling us how precise the number is. If the scientist didn't want these zeros included, they would have just left them off. They would have just wrote it as 0.002. You can't leave these zeros off because they are placeholders. But if those weren't necessary, they wouldn't be written in. But when they're written in, we then have 3 significant figures. So those are all the rules of significant figures. We're going to practice them a little bit, but does anybody have any questions conceptually on why these rules are the way that they are, or what we're doing when we're calculating significant figures? Okay, let's look at yeah, we'll talk about this real quick. Significant figures and precision is only something that applies to measured values. If you're using a piece of equipment to measure it, right? You have a ruler, you have a scale, you have a thermometer. There are certain things that are called exact numbers. Exact numbers have an unlimited number of significant figures. It means they're not limited by significance or precision. One example is anytime you're counting discrete objects. If you have 4 balls, it doesn't matter like how precise your equipment is, it's 4 balls, right? It's 1, 2, 3, 4. Your precision is your brain. You're using your brain to count 4 discrete objects. We don't have half balls. We don't have quarter balls. So we can't get like more or less. It's just 4 objects. Integral numbers, integral numbers that are part of equation are also considered exact numbers. They'd have unlimited sig figs. And then this says some conversion factors. For you guys, for this class, we're going to go with like almost all the conversion factors. Anytime you have an equality where 2 things are equal to each other, that's an exact definition. So 1 inch is equal to 2.54 centimeters. It's not just saying 1 inch with 1 sig fig. It's saying like 1.00000, and those zeros continue to infinity. All right. The most precise 1 inch you have ever been able to conceive in your life is equal to 2.54 with an infinite number of significance or 0 centimeters. So it's like right on the dot. Why that's important is when we're doing conversion factors later on, we're never going to use our conversion factor to limit the number of sig figs that we have. And if that doesn't make sense at this current moment, don't worry, we will talk about it. So let's look at some of these. All right, this one is wrong here. We'll go over that. Okay, so this first one, how many significant figures do we have? Just 2. Why aren't these zeros significant? They're not telling us anything about precision. They're not adding to the right side. They're just placeholders to let us know it's a decimal. This one here, 4 significant figures. The 1 and the 8 are significant. The 0 in the middle is significant because it lies between 2 significant figures. And then the 0 at the end is significant because it comes after the root number, after the decimal, telling us something about precision. This here, 4 significant figures. They're all non-zero numbers. That's an easy one. This here, 2.9, says that it's 3 significant figures. It's not. This is 2 significant figures, 2 sig figs. Okay, 2.9. If we wanted this thing to be 3 significant figures, we would write it as 2.90 times 10 to the 5th. That 0 after the decimal, giving us another level of significance. This here, 1 dozen is equal to 12. That's an unlimited number of sig figs. That's not going to become more precise. Like you can't get more exact than that. This guy here, lots of zeros. But all those zeros are significant, 5 sig figs. The decimal here means these are significant and the zeros in front are significant. And then we have this one down here, 100,000. This is ambiguous, or you could only honor 1 sig fig. Why? There's no decimal here, so I don't know if any of these zeros are significant or not. Can't tell the way that it's written. So I would only be able to honor 1 significant figure or 1 level of precision. So let's pull up a couple that I want you to work through. All right, so this worksheet is nestled in your Moodle page underneath the measurements worksheets, so you can find it there. I want you to do the top 2 rows, okay? I want you to look at these numbers, and I want you to tell me how many significant figures each one of those has. And I'll give you 2 minutes for that. Okay, so for this first one here, we have 1, 2, 3, 4, 5 significant figures. All of those values are significant because they're all non-zero. That's a pretty easy one to determine. This here, we've got a 1 that's definitely significant and an 8 that's significant. And then any of the zeros in between those are also significant. So all 4 of these are significant. This guy at the end here, I know the 7 is significant. I don't know if any of these zeros are significant. I can't tell the way that it's written. So I would write this as being either ambiguous or having 1 significant figure, just the 7. This guy here, all of those are significant. So 1, 2, 3, 4, 5, 6 significant figures, lots of significant figures in this one. This thing here, the 3 and the 4 are significant, and the 0 that comes at the end is also significant. These zeros are not significant. Why? They're coming before the number. Leading zeros, zeros before the main number, are just acting as placeholders. This last one here, all of these are significant. This internal 0 is significant. The 0 coming after the decimal is also significant. Any questions on those and significant figures? So in this first test section of class, I am teaching you significant figures. So my care for significant figures is great. I will be testing you directly on significant figures, and I'll have you do calculations where you have to round to the correct number of sig figs. As the semester goes on, my care for significant figures decreases, okay? Because the problems get more complicated, and it's like, we don't really need to waste all of our time on rounding to the correct sig figs. But for this first portion, you do really need to do this. So let's go back to the slides. We're gonna do something, it's going to seem real simple, but rules of rounding. Do you guys remember how you like would round a number? Hey, round it to the, second decimal place or something. When we're rounding a number, well, first of all, whenever you're doing any rounding, you always want to wait to the end of the problem to round. You don't want to round in intermittent steps. So if you have multiple steps, wait to the end to avoid what's known as a rounding error. So using only the last or the leftmost digit that's going to get dropped to decide in which direction to round. You want to ignore all digits to the right of it. So round down if the last digit dropped is 4 or less. Round up if the last digit dropped is 5 or more. So if we have let's say we write 86.54. How many significant figures does this number have? It has 4 significant figures, right? But let's say we have to round it to 3 sig figs. So we need it to be 3 sig figs because this is like the total and one of the factors only had 3 sig figs. So when rounding to 3 sig figs, I'm going to keep the 8, I'm going to keep the 6, and I'm going to keep the 5. Everything else is going to get cut off. The 4 tells the 5 to do what? Stay. All right, so this would round to 86.5. We just took something that had 4 significant figures, we rounded it to 3 significant figures. What if we have 102.6, and I want you to round this to 3 sig figs? I'll have you do that. Okay, so we're going to keep the 1, we're going to keep the 0, and we're going to keep the 2. Everything else gets dropped. What does the 6 tell the 2 to do? It tells it to round up. So this would become 103. Is that ringing some bells from like math back in elementary school, rounding up, down? Okay, cool. I don't want to insult your intelligence, but I do want you to round correctly. Round this 4.449. Round this to 2 sig figs. So in this case, we're going to keep the 4 and the 4. Everything else gets dropped. The 4 tells this 4 to stay, so we round to 4.4. What happens sometimes is students will go, oh, well, doesn't the 9 tell the 4 to round to 5? And then the 5 tells the 4 to round to 5? No, don't do that. Don't play that game, because how far back do you have to go then, right? So what if it was 4.444449? You have to go all the way back there and do that? No, we ignore that as junk information. We just look at the number that comes right before it. So why do we care about rounding? What does this have to do with anything? Well, when we're doing calculations in science, and we have 2 numbers that we're going to multiply or divide together, multiplication and division are at the same level of like our order of operations. They're kind of like brother, sister to each other, or opposites of each other. So anytime you multiply and or divide a number, the resulting number will have the same number of significant figures as the factor with the fewest number of significant figures. So have you ever like put 2 numbers into a calculator and multiplied them together, and then you get this number with like all these decimal places, and you think, how many decimal places does this teacher want? Do I give them all the decimal places? I don't know. Well, now you know what to do, at least for measured values. So this is the idea is like you're only as strong as your weakest link, or your final answer is only as precise as your crappiest piece of information. So look at these. We're going to multiply these 3 numbers together. This thing has 3 sig figs. This thing has 5 sig figs. Look at this. This has 2 sig figs. This is like garbage. So You plug it into your calculator, you get this number with all these decimals. Oh, look at how precise my number is. No, we only get to round or use two significant figures because we're only as precise as our least precise piece of information. That is also for division as well. So I've got 5.892 divided by 6.10. We plug this into our calculator. We get a big long decimal. How many significant figures can I use? I can only use 3 significant figures. I don't get to use the full 4. This is the crappier piece. So we go with 0.966 because the 9 here tells the 5 to round up. So multiplication, division, go with the least number of significant figures. Let's find that worksheet again, and we'll do have you guys do a couple on your own. We'll skip over addition, subtraction here. All right, do A, B, C, and D. So I want you to plug these into your calculator, get an answer, but not just the answer. I want you to then round it to the correct number of significant figures. I'll give you 2 minutes. It shouldn't take you more than 30 seconds for each one. Okay, so looking at this first one here, we'll get a number. Calculator pops out something quite long, like 6.23684, kind of so on and so on. I only get to use how many sig figs? 2 sig figs. This has 3, this has 2. So I get to keep the 6 and I get to keep the 2. I would round it to 6.2. Questions on that? No, you like that?
I think the result is 90.06.
Oh, sorry. I was dividing them by each other. I saw your faces in the boxes looking at me, questioning. That's why I asked. Yeah, if I if I ever get those wrong, let me know. I don't know why I wanted to divide it. 23.7 times 3.8. I swear I can plug things into the calculator. Yeah, there we go. 90.06. Okay. So we get to have 2 significant figures, this and this. We cut off the rest of it, 90. That makes you guys happier? Yeah, your faces look happier there. Okay.
Would you have to write the decimal point?
Yeah, you would want to include the decimal to, I guess, to indicate that the 0 is also significant. Yeah, that would be the more precise way of doing it. 45.76 times 0.25. This thing gives us 11.44. How many sig figs do we get again? Just 2. So we would round this to 11. 81.04 times 0.0. This guy gives us 12.2504. How many sig figs do we get to keep? Just 2 here. So we would round this to 12. That last one, 6.47 times 64.5. Get 417.315. In this case, 3 sig figs. We'd round it to 417. let's do this here. Let's say we take 6.0 grams and we divide it by 2.00 grams. Okay, I want you to give me an answer with the correct sig figs. Okay, so if you were to plug this into your calculator, what are you going to get? You're going to get a value of 3. But how many significant figures do we need? We need 2. 2 sig figs here, 3 sig figs here. We have to have 2 sig figs. So how do I make 3 with 2 sig figs? I add a 0. If you ever need to create more significance, throw some zeros at the end. Let's see. Sorry, someone said they got something different for C, and I think I messed that up too. I have done 2 lectures today already, and my brain is a little shot. 81.04 times 0.010. Yeah, this is no good. We're going to go with 0.8104, and we'll keep 2 sig figs. So it would round to 0.8, 0.81 would be our value. Thank you, Cynthia. So multiplication division, which is where you're going to spend like 95% of your time in this class, is going to honor the lowest number of significant figures. What happens if we look at addition, subtraction? So addition, subtraction. Which, addition, subtraction are in their own level of order of operations underneath multiplication, division. In addition, subtraction, forget significant figures, just look at decimal places. So you are the resulting answer is going to carry the same number of decimal places as the quantity that has the fewest decimal places. Okay, it's all about decimal places. So remember when you guys used to add and subtract and you'd line it up like this as a little kid and you'd put like the decimals on top of each other? Well, you may want to do that when going through this because then you can visualize where you're going to cut the number off. So this first one has 2 decimal places. This has 3 and this has 3. We're going to cut it off at the second decimal, right after the second decimal place, because this guy only has 2. So when we add these together, we get 9.214, but we're going to cut the 4 off and just honor 2 decimal places, 9.21. Doesn't have anything to do with significant figures. Same thing with subtraction, 4.8 minus this 3.965. Cut it off at the tenths place. Our resulting answer, which we had 0.835, is now going to just be 0.8. So don't use the decimal rule for multiplication, division, and don't use sig figs for addition, subtraction. Make sure to keep those separate. If you have a problem where you have multiplication, division, and addition and subtraction, always make sure you do what's in parentheses first and don't round until the very end. Let's do an addition, subtraction. Scroll back up to here. So you've got these three, they're all additions. So do these. Add them together and then round them to the correct number of sig figs. And I'm gonna like try my best to add these numbers correct. All right, so the first one here, we got 169.0237. I'm gonna cut it off at the 10th place. So 169.0. All the other stuff we kind of just consider junk information. Right, this next one, we got 582.818. Now we are going to cut off right at the tens place again, the 10th place again. So we'll cut off here. The one tells the 8 to stay. So 582.8. All right, this one, we get 2026.8378. Again, we cut it off at the 10th place. So we get to keep that 8. The 3 tells the 8 to stay. So 2026.8. Any questions on that? All right, we'll keep moving forward then. So up until this point, all of the numbers that I've been writing out or that we've been looking at have sort of been meaningless numbers because they haven't had any units to them. So in chemistry, from like this point forward, you're not going to see a whole lot of numbers just written without any sort of unit. I want to know, like, are you talking about distance? Are you talking about volume? Are you talking about time? And so we need to add a unit to the numbers. You guys are probably more comfortable with the British system, which is pounds and miles and feet. It's a messy system. Like how many feet, or rather, how many inches are in a feet? 12. How many feet are in a yard? 3. How many feet are in a mile? 5,280. How many yards are in a mile, right? Like none of those numbers are really congruent with each other. It's messy. Now, the metric system, which they use pretty much everywhere else, is all going to be on a base of 10. So if you have a meter, how many decimeters are in a meter? 10. How many centimeters are in a meter? 100. How many millimeters are in a meter? 1,000. 10, 100, 1,000. They're all base 10, which makes it really convenient and easy to convert between them because you can just move the decimal place around. You can't do that with the British system. So the international system of units, or the SI units, or the standard units that they use in science throughout the whole world, are going to be in these more appropriate British units, or rather metric units. So the length is going to be in a meter, mass is actually in a kilogram, but the base is a gram. Time is in seconds, and temperature is in this thing called Kelvins, which relates directly to Celsius. We'll look at that a little later. So we don't need to get into all this. Okay. One thing to note, what's the difference between weight versus mass? So a kilogram is a measure of mass, which is different than weight, which would be in pounds. Mass is the amount of matter contained within an object. Like how many atoms, how much stuff does it have? Weight, on the other hand, is the effect of gravity on that specific amount of matter. So when you weigh yourself, you're not actually getting a value that tells you about how much stuff is in you. You're getting a value of how gravity is pulling on your stuff. Okay, so weight is dependent on gravity. If I had, you know, your body mass on Earth, and then we took you to the moon, you would, quote unquote, weigh less because the gravity is less. So the thing that's nice about the metric system is, in order to change out a unit, or like, let's say we're dealing with meters and we want to make a bigger unit, we can just tack on one of these prefixes. If I want to make a smaller unit, I can also do the same thing. So when looking at this chart, your base unit is going to go right. I don't have it written in here, but it's going to go right in here. Okay, so this is where your base unit goes. What's an example of a base unit? A gram, a meter, a liter, a second, a joule, there's some other ones. So like gram would be a base unit. If I wanted to make a unit that was the size of 10 grams, then I would go up one and it would be called a decagram. If I wanted something that was 1,000 grams, we'd go up 3 hops, it would be a kilogram. All right, what about if we were moving in the other direction? Let's say we use meter. If I want something like the length of 1/100th of a meter, I'm going to hop 2 spots. That's going to be a centimeter. Century. Millimeter is going to be 1,000th, a millennial, 1,000 years. So this is really useful. They get bigger than kilo and milli. Once you get past kilo and milli, these values go up not just by 1 factor of 10, but they go up by a factor of 1,000. Do you see how it's a chunk of 3 zeros? That increases. It's 10 to the 3rd, then 10 to the 6th, to the 9th, and to the 12th. So I'm sure you guys have heard of like a mega, well, maybe you haven't heard of a megabyte. Maybe that's like so old school, but they used to have iPods, not even iPhones, but iPods that had just music on them. And they had like a certain amount of megabytes, right? Gigabytes, terabytes. A lot of times like external hard drives now are terabytes. It's just a crazy amount of information, trillions of bytes. We won't use these guys quite as much. Then there's like the smaller ones, micro, nano, pico, femto. We spend a lot of time here. So I'm going to give you alliteration for this thing. King Henry died before drinking chocolate milk. Okay, so let's put it on our whiteboard. King Henry died before drinking chocolate milk. So king is representing the kilo. Henry is the hecto. Died is deca. Before is base unit. Okay, so your base unit is included in this. So that can be, again, gram, liter, meter, second, so on. Deci is, or rather drinking is deci. We've got, and this is, again, we're following this right here. Okay. So then we've got our chocolate, which is centi. And then our last one, which will be milli. Now, if you write it in this order, King Henry died before drinking chocolate milk, it's really easy to convert between these. Okay. Let's say that you're given that you have 38.6 kilometers. And I want to know how many meters that is. Okay. If we were dealing with miles and inches, we have to set it up in dimensional analysis and use conversion factors, which we'll get into later. But this, we can just use some hops. So let's figure out, where are we starting? What is the unit we're starting with? The kilometer. So we're starting over at King. Where are we ending? At the meter. We're ending at the base unit. Okay. How many hops does it take to get over there? 1, 2, 3 hops to the right. So what I do is I take my decimal, this 38.6, and I hop the decimal over 1, 2, 3, and fill those in with zeros. 38,600 meters are contained within 38.6 kilometers. Isn't that nifty? Way more useful than 12s and 3s and 5,280s. So let's say that we're given that we have 1,412 centimeters. And I want to find kilometers. Okay, it works both ways. So we're starting with a centimeter. That's over here at the chocolate. We're ending at the kilometer, which is over here at King. And we figure out how many hops. We go 1, we have to go through the base. So 2, 3, 4, 5 hops to the left. Where is the decimal right now? It's sitting here. I'm going to move it 5 hops to the left. 1, 2, 3, 4, and 5. And we fill that in with a 0.01412 kilometers. It works for grams and kilograms. It works for liters and milliliters, all of them. So we like this. We like the metric system. It's just neater. As far as when to pick a prefix, like what you should use, pick a unit that's similar in size or smaller than the quantity that you're measuring. So let's say we have a short chemical bond, which is 1.2 times 10 to the negative 10th meters. And we've got a pico, which is 10 to the negative 12th. And then we've got a nano, which is 10 to the negative 9th. We would go with the pico, the smaller unit, and it would work out to 120 picometers. We're not going to do, I'm not testing you guys really on those numbers, picos and nanos, but within the boundary of King Henry died before drinking chocolate milk, you definitely want to be able to move through those, convert through them. Volume is kind of an interesting unit. There's a couple different ways that we talk about volume. We can measure volume in liters or gallons, but we can also have volume as what's known as a derived unit. And a derived unit is a unit that comes from other units smushed together. So what is volume? It's a space. It's length times a width times a height. So some examples of volume could be the cubic meter, right? Or meters cubed. The cubic centimeter, centimeters cubed. If you've ever been in a hospital setting and you've heard of a CC, that's a cubic centimeter. Okay, it's a centimeter by a centimeter by a centimeter box. We can have cubic millimeters. If you've ever gotten mulch delivered to your house, it usually gets delivered as cubic yards, right? A yard by a yard by a yard, some sort of volume. So volume can have lots of fun units. So this is convenient. King Henry died before drinking chocolate milk when we're using the metric system. But what happens when we're not using the metric system or we have things that aren't so direct? We have to set things up in dimensional analysis. All right, so unit conversions. So whenever we're problem solving, and I feel like a lot of what we do in this class is just glorified unit conversions. It's converting from one unit to another. We aren't using an equation per se. We're setting it up as a unit conversion, and it requires this thing called critical thinking. And I can't give you critical thinking. Critical thinking is something that you kind of build. It's like a muscle that you strengthen. And how do you strengthen it? Through doing practice problems. So you need to do the homework, you need to do the assignments, and that will help you to enhance your critical thinking. Because the example problems that we go over in class here are showing you like the basic concepts, but it doesn't mean that on your test, it's going to be the exact same problem or worded the exact same way, right? So you have to be able to sort of take every problem on and use your critical thinking to sort of find out where you need to go and what you need to do. So we do both unit conversions. This is, I feel like, a lot of what we do, or we have equations. You guys are probably more comfortable with this, where like you get an equation, it has 5 variables, you're given 4 of the 5 and you solve for the 5th. You guys remember that in like basic algebra? Yeah. So that you're probably pretty comfortable with. This one may feel a little bit foreign, so we're going to spend some time on that. So we use this thing called dimensional analysis, which is just a fancy way of setting up a problem in such a way that you have units and they multiply and divide in such a way that the units will cancel out that we don't want, and the units that we do want will stay around. We always use the units as our guide to solve these things. We always want to make sure that we put a number with its associated unit. So don't leave the number off, don't leave the unit off. Don't let units just randomly appear or disappear in a calculation. That doesn't work. Okay, so this is like the basic skeletal structure of dimensional analysis. You have a given piece of information, you multiply it by some sort of conversion factor. And what is a conversion factor? A conversion factor is an equivalency or any two things that are equal to each other. So 1 foot is equivalent to 12 inches. That's a conversion factor, okay? 1 meter is equivalent to 100 centimeters. That's another conversion factor, okay? 2.54 centimeters in every 1 inch. That's another conversion factor. How many conversion factors are there in the world? Oh my gosh, there's so many as there are units and combinations to do that. So you don't need to memorize the actual conversion factors. You just need to be able to like reference them. So we take our information that's given, we multiply it by a conversion factor, and we get our information sought. Or it looks something like this. We have our given unit, we multiply it by the conversion factor in such a way that the given unit sits on the bottom of the fraction bar and the desired unit sits up on the top. What will happen is the given units will cancel and you'll be left with desired units. That is, sounds more complicated than it actually is. So let's look at an example problem. And hopefully that will make it a little bit clearer. So let's say that we're given that we have 3.72 feet. And I want to find how many inches that is. Okay, and I know that you probably can just do this in your head and say, oh yeah, well, feet, inches, I'll just multiply it by 12. But I want it to be set up in dimensional analysis. So if we're doing it in dimensional analysis, if we're doing a conversion factor like this, we need a relationship between feet and inches. So what is that relationship? 1 foot is equivalent to 12 inches. We can write it like this, or we can write it as a fraction. We can say 1 foot divided by 12 inches. Because these two things are equal to each other or equivalent to each other, anything divided by itself is 1. So when we use a conversion factor, we're not changing the number value, we're just changing its units. So we could write 1 foot over 12 inches, or we could write it as 12 inches over 1 foot. Now, which one do you use? That's really dependent on what you're starting with and where you're trying to go. So we are starting with feet. So that's my given information is I have 3.72 feet. I want to multiply this by a conversion factor. And remember from this slide here, we want the given unit to be on the bottom of the fraction bar so those two things cancel out. So if we're looking at these, feet are here, so I want feet on the bottom. So I'm going to use this. All right. 1 foot for every 12 inches. What happens to the unit of feet? Those cancel. And then you just do the calculation. So anything that's on the top of these fraction bars is multiplied together. Anything that's below a fraction bar, it's divided. So we're going to take that 3.72 and we're going to multiply it by 12. And I know you were like maybe thinking, oh, well, obviously you multiply it by 12 because you're comfortable with feet and inches. But if you're dealing with something that you're not as comfortable with, or the conversion factor isn't as intuitive, you want to be able to set it up in dimensional analysis. So the unit that's left is inches, right? And my number is 44.64. I only get to honor 3 sig figs. Remember, conversion factors have unlimited sig figs. Okay, so we're going to go with the given piece of information, which is 3 sig figs, and we get 44.6 inches. I'm going to have you do one. Let's say that we're given that we have 18.5 inches, and I want to find centimeters. And I'm going to tell you what the relationship is. Okay, 1 inch is equivalent to 2.54 centimeters. Right, that is your conversion factor for this problem. So I'll give you 2 minutes to set it up in dimensional analysis in that structure where you cross units off. Okay, so here's my conversion factor. I'm going to write it as a fraction. The 1 inch is equivalent to 2.54 centimeters, or we could use 2.54 centimeters is equivalent to 1 inch. Which one we use is dependent on which direction we're going. Are we going from inches to centimeters or centimeters to inches? So we start with that given 18.5 inches. Always start with your given information, multiply it by the conversion factor. So I like the idea of using this one. Oops. Because then I can get rid of inches and I can move into centimeters. So the 1 inch goes on the bottom, the 2.54 centimeters will go on the top. Then you just we cross out the inches and you just do what it tells you. So this says to multiply those two things together, 18.5 times the 2.54, and we get 46.99, 3 sig figs, 47.0. And the unit on that is a centimeter. Why don't we do one with these same things, but let's go the other direction. Let's say that you're given that you have 192.3 centimeters, and I want to find how many inches that is. Okay. I'll give you 2 minutes for that. Okay, so this one uses similar information, but the setup is slightly different. We have 192.3 centimeters. We want to go to inches. So you can even just go ahead and put the centimeter on the bottom and the inch on the top, because you know that's how, we want the centimeters to cancel, and then just fill in the information. So 1 inch is equivalent to 2.54 centimeters. We take our initial value, 192.3, and we're going to, in this case, divide it by the 2.54. Some people will think, oh, well, when I'm going from centimeter to inches, I divide. When I go for inches to centimeters, or other way, I multiply. I just set it up in the dimensional analysis and let the setup tell me what to plug into my calculator. So in this case, we get 75.71. We're going to go with 4 sig figs inches. Sorry, I'm sort of trailing off there. I don't want to color on your faces. Is that making sense, the setup for dimensional analysis? Yes, there are certain problems where you probably won't have to set it up in dimensional analysis, like feet to inches. But for other stuff, it's a good thing to have. Let's do, before we go, let's do a 2-stepper. So how many feet are in 1,824 centimeters? Okay, this is a 2-stepper because, and I'm going to draw a solution map here. So we want to go from feet into inches. And then from inches, we want to go into centimeters, right? Because there isn't really a great conversion between feet and centimeters. So 2-stepper, I'm going to let you try and work on it. I'll give you 4 minutes and then we'll reconvene. Okay, so this 2-step problem, we can start with our given 1,824 centimeters. Actually, I wrote this backwards. We want to go centimeters to inches, inches to feet. Hitting my edge here. This is the last problem we're going to do for today, just FYI. So centimeters to inches and then inches to feet. That makes more sense. So if I want to go centimeters to inches, I can use that conversion factor from the previous thing that said, hey, 1 inch is equivalent to 2.54 centimeters. And from there, we know that 1 foot is equivalent to 12 inches. Some people will break these up. I just chain mine together. So the centimeter cancels, the inch cancels, and we'll be left with just units of feet. So 1,824, we're going to divide that by the 2.54, and then we'll divide it by 12. And we end up with 59.84 feet. How many of these could you chain together? You could chain a bunch of them together. It's really dependent on the problem, on what is it asking and what is it trying to find. So that's where the critical thinking comes in. Now we are going to stop there. We'll do some more practice with dimensional analysis next week. And then we will do a little bit more from this chapter with density. So you don't have chapter 2 homework yet. You have the syllabus verification due on Sunday. And then you also have your chapter 1 homework, which is just kind of getting you comfortable with mastering chemistry. So make sure you get those done by Sunday. Monday, we won't meet because that's lab time. Unless you want to meet, send me a message. Otherwise, enjoy your week, and I will see you guys next Wednesday at 6 o'clock. So have a good evening. Bye. And if you have any questions, feel free to stay around.
I got a quick question.
Yeah.
Just with that last problem, it doesn't matter with the significant figures with that, or is that just like the arbitrary like 59.84?
So you're in that one. Hold on. So the given information had 4 sig figs. So that's why I went with 4 sig figs.
Okay, cool. That's it.
Yeah. Yeah. Other
I
people?
have a question about that same problem.
What's up?
So would it be possible, you said that you took 1824 and then divided it by 2.54 and then divided it again by 12. Could I multiply the bottom, the 2.54 times 12, and then divide it into 1824?
That's fine.
Do you think
Yeah.
that will come up with the same answer every time?
You'll come up with the same.
Or okay.
Yeah, you could multiply all the things underneath the fraction bar and then divide by that. Yeah.
Okay, great. Because yeah, it's been a while since I've had math.
So
just
yeah,
making
you can do
sure.
that as well.
Okay.
Other questions?
I had a question when it comes to rounding numbers.
Okay.
If they let's say we have a number that ends in 4, like the answer in this last problem, 59.84. If they just ask you to round, you could leave it as 59.8. But if they ask you round to the nearest 10th, would it be 59.7?
No. So
Or would it
so for this one, let's say we wanted to round to 3 sig figs. If we wanted to round to 3 sig figs, the 4 is going to tell the 8 to stay. So 59.8. If we wanted to round to 2 sig figs, the 8 would tell the 9 to round up, which would round that up, and it would be 60. Hello?
okay?
You there? Sorry, my internet's getting unstable.
Yeah. Yep.
Okay. Other questions?
That's I understand if they ask a number of significant figures. I was just confused because I was asked in other math classes to, like, if it was rounded to a specific decimal point, then the number would actually round down.
So
If
you
it
would
was
have
equal to or
like-
less than 4.
like you would round it down. No, we're going to let it stay. We're going to keep it as is. We're not going to round it down.
Awesome.
Okay.
And I sent you an email regarding mastering chemistry.
Okay.